Ever wondered what happens to information that falls into a black hole? It's one of the biggest mysteries in physics. Imagine if we could actually retrieve that info. Sounds like science fiction, right? But hold on tight, because quantum teleportation might just make it possible. A recent study suggests that quantum teleportation could help us retrieve information from a black hole. When we talk about quantum information, we're dealing with qubits. Unlike classical bits that are either 0 or 1, qubits can exist in a superposition of states, kind of like being both 0 and 1 at the same time. The study, led by Adam Jermyn from the University of Cambridge, explored this idea. They developed an algorithm suggesting that you could, in principle, retrieve some quantum information from a black hole. But here's the catch, it's just one qubit, and extracting that qubit might mean you can't get any other quantum info out. Now, don't go tossing your computer into a black hole just yet. We're talking about theoretical physics here. The practical application of this is still a long way off. This idea also touches on the infamous black hole information paradox. The paradox suggests that information falling into a black hole could be lost forever, conflicting with quantum mechanics principles. But if we can retrieve even a tiny bit of quantum info, it challenges this paradox. In the 1970s, physicist Stephen Hawking predicted how this might work. Because quantum particles act like waves, their position is described as a probability range of all locations, including positions both inside and outside the black hole. Thus, it remains possible, though improbable, for some subatomic particles to use quantum tunneling to escape a black hole. In this case of quantum tunneling, quantum radiation leaks from the edges of a black hole in a process dubbed Hawking radiation. This radiation is thought to be incredibly dim, so dim in fact that it has never been detected, though most scientists are confident it's real. By taking precise before and after measurements of the black hole's mass, scientists can calculate the mass of the lost particle. This measurement is considered classical information. But things get trickier when we enter the realm of quantum mechanics. Unlike classical bits, which are either 0 or 1, qubits exist in a state of superposition, meaning they can represent multiple states simultaneously. However, the very act of measuring a qubit forces it to choose one state, thereby eliminating the other potential information it carried. To illustrate this, let's consider a piece of quantum information like the spin, or angular momentum direction of a particle thrown into a black hole. Classically, a black hole may have a single angular momentum. But in the quantum world, this angular momentum can be described as a superposition of multiple possibilities. Jermyn and his colleagues have been working to deduce how a single piece of quantum information, such as the spin of a particle, behaves when it interacts with a black hole. According to Hawking radiation theory, two new, ghostly particles are created in response. One is consumed by the black hole, and the other escapes. By examining the state of the outgoing particle from the Hawking radiation, physicists could theoretically deduce information about the incoming particle. Here's where it gets even more fascinating. The trick is to do all this without looking. Directly measuring the spin state of the outgoing Hawking radiation forces it to choose a spin state, thereby losing the quantum information it carries. These non-measurements provide some information, but not so much that all the quantum mechanical information is lost. This approach allows researchers to back-calculate the angular momentum spin orientation of the original qubit that fell in. Essentially, this shows how, in theory, someone could retrieve quantum information from a black hole. Now let's talk about the practical applications of this groundbreaking method. While the theoretical framework is fascinating, its real-world applications are limited to say the least. For one, you can't accidentally throw a qubit into a black hole and then say whoops and try to get it back. This process requires planning and precision. Jermyn explains that people who accidentally wiped their data by tossing it into a black hole would be out of luck. Their method retrieves just one qubit of information, and it's unlikely that much more could be retrieved even if the algorithm were developed further. Beyond that, physicists don't even agree in theory on how much data could be retrieved from a black hole. It's possible the information escapes in the same fashion that, when you delete a file on your computer, technically the information still exists. It's just been scrambled. It's also possible that there's a fundamental limit on how much you can get out before it gets scrambled beyond recognition. And let's not forget the practical challenges. The nearest black hole is too distant for scientists to test the algorithm. But in principle, scientists could create tiny black hole analogs in the lab, using supercooled aggregates of particles known as Bose-Einstein condensates. In that case, scientists would use voltage to create an impermeable divide, similar to a black hole. Such systems could be used to probe some of these theories about black holes.